Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 23rd lecture for the series of lectures on advanced computer architecture. Today, our focus of discussion will be software support at compile time. Today, after a brief review of what we have talked about, the hardware and software-based instruction level parallelism, we will be talking about the hardware support at the compile time, which basically covers the conditional or predicated instructions and the use of hardware-based speculation at the compile time. In respect of the exploitation of instruction-level parallelism, we have studied two different techniques, that is the dynamic scheduling and static scheduling. These techniques are used to exploit instruction-level parallelism for single or multiple issue of instructions per clock cycle, and we discussed in detail how these methods can be used to enhance the overall performance of a processor. While talking about the dynamic approaches, we said that the hardware modification is made which ultimately resulted in the development of superscalar and very long instruction word processors. Furthermore, we discussed that the pipeline structure enhancement, such as Tomasello's pipeline and the branch prediction techniques. The Tomasello's pipeline technique is one where we modify the structure, improves the number of functional units so that the structural hazards and data hazards are overcome. While talking about the branch prediction, we discussed the techniques to minimize the stalls due to control hazards, and then we combined the Tomasello's modification with the branch prediction, and we developed the overall design of the system for dynamic scheduling. Whereas while talking about the static scheduling, we discussed four basic approaches, that is the loop unrolling, software pipelining, trace scheduling, and superblock scheduling. We found that these techniques are focused to increase the instruction level parallelism by exploiting processor issuing more than one instructions every cycle. These techniques give better performance when the behavior of the branches is correctly predicted at the compile time. However, otherwise the parallelism could not be completely exposed at the compile time. This is due to the following two reasons. Number one, the control dependence, and number two, the dependence between the memory reference instructions. The control dependence limits the amount of parallelism that can be exploited, and the dependence between memory reference instructions could prevent the code movement necessary to increase parallelism. These limitations, particularly for very long instruction word processor, could be overcome by providing hardware support at the compile time. Now, today, we will discuss some hardware support-based techniques to help overcome these limitations, and secondly, to expose more parallelism at the compile time. The most commonly used such techniques include instruction set enhancement and hardware speculation. The enhancement or extension in the instruction set is made by including conditional or predicated instructions. Predicated means something based on something, which means that we predicate the instruction, we develop the instruction such that it takes into consideration what is something based on which something else has to happen. Whereas the hardware speculation to enhance the ability of the compiler to move code over branches while preventing exceptional behavior of the instructions or of the code. Moreover, this allows the compiler to reorder the load or store instructions when no conflict is suspected, but the conflict is not certain. Now, these extended instruction sets include conditional or predicated instructions which allow the compiler to group instruction across branches. That is, the instructions across branches, they are combined in one group. And this results in the elimination of branches, because when more than one instructions in different branches are grouped together, the branches can be eliminated. This extension in the code further helps to convert control dependence into the data dependence. These approaches are equally useful for hardware-intensive as well as the software-intensive schemes, that is, both for the dynamic scheduling as well as the static scheduling. Now, as we discussed earlier, that predicate registers are included in the structure of the IA64 processor. This we discussed when we talked about the dynamic scheduling, and in our concluding discussion, we discussed the use of predicate registers. This predicate register is used to implement predicated instructions to improve the overall performance of the processor. Now, let us discuss the concept behind introducing the conditional or predicated instructions in the instruction set of the processor. The basic concept is that the conditional instructions are introduced with extra operands. This extra operand is basically a 1-bit predicate register. A condition is evaluated as part of the instruction execution to set the value of predicate register. In the HPL-PD processor from the HP lab, the value of predicate register is typically set to the operation namely compared to predicate. This instruction can be expressed as P1 equal to compare predicate less than or equal to R1, R2. Here, in this expression, the predicate register P1 is set to a value 1 if R2 is less than or equal to R1. Now, this basically represents that if the condition is true, that is P1 is equal to 1, then the instruction is executed normally. Otherwise, that is when the condition is false, which means that when P1 is equal to 0, the instruction execution continues as if the instruction were a no operation. Now, this concept is used in the design of some new instructions. Here, I'll give you some typical examples of the instructions for a pipeline processor. For example, let us first of all consider the conditional or predicated move instruction. In MIPS architecture, this move instruction can be written as C move Z, where this instruction specifies that it is a conditional move if the additional register has got a value equal to 0. And we can write this instruction as, say, CMOV-Z, which stands for C move 0, followed by the names of 3 registers, that is R1, R2, R3. This instruction, when it is executed, it moves the value from one register to another, say from register R2 to register R1, provided the condition is true. That is, the third operand, R3, is 0. So, such instructions are used to eliminate the branch code sequence. Here, similarly, another example can be for a conditional add instruction, which you can see here can be written as R8, which is in fact the predicate register, followed by the normal add instruction, which says add R1, R2, R3, means that the sum of R2 and R3 is placed in register R1 only when the predicate register R8 is 1 or is set. This register may be set by some previous instruction. The other example can be that of a conditional load instruction. A conditional load instruction can be written as load word conditional, which is LWC, followed by the register where the data is to be loaded and the memory location, which is 0R2 in this case, that is from the offset value given in register R2, and the corresponding memory address. The value is to be read and loaded into the register R1 if the predicate register R3 is 0. Here it assumes that the load occurs unless the third operand, that is the predicate register R3 in this example, is 0. In case of the load word instruction, the load word or a short block code, so it is either one word which is to be loaded, or it may be a short block of codes which may be contained for this purpose, followed by the branch, can be converted to a load word conditional instruction, and it can be moved up to some higher issue slots to improve the execution for several cycles. In order to explain this, let us consider this example code. Here we will consider this conditional statement, that is, if a is equal to 0, then place the value of t into s. That is, the value of s is to be replaced by t only if the value in a is 0. Here, in order to implement this statement in a coded form, we may assume that the register R1 holds the value of A, register R2 holds the value of S, and register R3 holds the value of T. Considering this assignment, the code to implement this conditional statement can be written as shown over here, where the first instruction is branch if not equal 0. R1 comma L means that it should perform no operation if A is not equal to 0. As you can see from here, the branch location L is outside from the next instruction. And the second instruction here is basically the else part, which is add unsigned R2, R3, R0, means that add the contents of R0 to the contents of R3. R0, as you know, in the MIPS architecture is assumed to be the register which always holds a value equal to 0. So adding 0 to the contents of R3 and then placing this value into the register R2 is basically equivalent to replacing the value of S, which is in R2, by the value of T, which is in R3. Now the if statement can be implemented by using the conditional move instead of using this branch instruction and the add instruction. The equivalent conditional move instruction is, as shown over here, C move Z, R2, R3, R1. Here, the third register R1, in this case, represent the predicated register. So this instruction will move the contents of register R3 into the register R2 only if the third register contains the value equal to 0, which is in fact the required condition. That is, if R1 is equal to 0, this means that if A is equal to 0, the contents of register R3, which is equal to T, will be moved into register R2, which is equal to S for this example. Furthermore, you can notice that using this conditional move instruction, what we have done is that the next operation is determined by the contents of the third register instead of executing the condition. So basically, this process is equivalent to converting the control dependence into the data dependence. The control dependence means that the if conditions evaluation, this has been converted into the data dependence, that is the contents of register R1 or the predicate register. So this in fact makes the whole process very simple, where instead of spending time in the condition evaluation, it is only data dependent operation which has been made. Basically, this transformation has moved the place to resolve the dependence in a pipeline processor. We know that in a pipeline processor, the dependence for branches is resolved near the front of the pipe. This actually means that whatsoever is the first instruction in the pipe, if that is a condition instruction, it will be evaluated to resolve the dependence. Whereas by using the conditional instruction, we resolve this dependence when and where the data register occurs. Now this transformation is also used for a vector computer. We mentioned about the vector computer earlier, where in this particular type of computer, we call this process of transformation of the location to resolve the dependence as the if conversion. That is, the if conversion replaces the conditional branch with predicated operation. For example, we can see the code generated for the following two if-then statements here. Here you can see that there is first block of if-then-else statement, which says that if A is less than B, then we have to replace C by A. Otherwise, C is to be replaced by the value of B. Similarly, the second block says that if D is less than E, then F is to be replaced by D. Otherwise, it is to be replaced by E. Now we can convert these two blocks of instructions by using the if conversion process, which can be written for a very long instruction word processor's format by using two instructions as shown over here. Here, the first statement contains 4 instructions, where each of these instructions in the very long instruction word packet, it evaluates the condition and it updates the predicate registers P1, P2, P3 and P4 for 2 different aspects of the condition evaluation. That is, P1 is updated if A is less than B, and P2 is updated for A greater than or equal to B. Similarly, the other 2 operations, they represents the values which will be placed in the predicate registers P3 and P4. Now these predicate registers are used in the following very long instruction word statement by placing 4 operations in one statement. And these 4 operations in a statement are: the value of C is to be replaced by A if P is equal to P1 is equal to 1, whereas C is to be replaced by B if P2 contains a value equal to 0, and similarly F is to be replaced by D or E depending upon the contents of the predicate register T4 and P3. However, the same operation can be alternatively implemented by using a compare instruction which compares for two different values, that is for the true behavior as well as for the false behavior. This you can see from this example statement where P1, P2 is updated with the help of one compare operation for condition to be true and condition to be not true for the values contained in registers R1, R2, and this way the very long instruction word for the two if blocks can contain only two compare instructions instead of 4 as in the first case. However, these are two different approaches which are usually used for very long instruction word processors. We can look into some other uses of conditional move instructions. This is another example where you can observe that a conditional move is used to implement the absolute values. That is, if we have to convert a value given by B into its absolute form and place this absolute value in a variable A, then this particular conversion is possible by using this type of if statement, that is if B is less than 0, which means that B is negative, then A is to be replaced by minus B. Otherwise, A is to be replaced by B. This is basically what do we mean by the absolute value of the function. Absolute value of the function of any variable or any number is always a positive value. So this is why if the original value of B is negative, which means if the B is less than 0, then its negative value is to be placed in A, which is in fact the equivalent or the corresponding positive value. Now this can be implemented by using either very long instruction word as we discussed earlier, or by using the conditional move instructions as you can see over here. Here we can use the pair of conditional move instructions like C move Z, R2 minus R3, R1. This actually means that the value of minus R3 will be moved into the register R2 if the value contained in the predicate register R1 is equal to 0. Similarly, the second conditional move instruction, C move Z, R2, R3, R4, replaces the contents of R2 by the contents of R3 if R4 is equal to 0. However, this operation can also be implemented by using one unconditional move instruction to replace the value of A by the value of B, whereas the second instruction must be a conditional instruction which should replace the value of A by minus B when the predicate register is equal to 0. The conditional moves, therefore, enables us to eliminate the branch and improve the pipeline behavior, because this basically reduces the condition evaluation process. It is useful for short sequences. However, it has certain limitations, and these limitations are: when prediction is used to eliminate branches, those branches which guard the execution of large blocks of codes, many conditional move operations may be needed. To remedy this inefficiency, some architectures support full predication, that is, the execution of all the instructions is controlled by predicated moves. The full predications allow to convert the large blocks of codes that are branch dependent. Here, let us consider an example of if-then-else statement within a loop converted to predicated execution. Here, the code executes only if the value of the execution is true, and the code in the else case executes only if the value of the condition is false. Here, it is an example where we can consider the case of two code sequences for a two-issue processor. Assuming that this two-issue processor is superscalar, it can issue a combination of one memory reference and one ALU operation, or a branch operation by itself in every cycle. Let us have a look onto this code, where you can see that in this code, the first instruction slot has got a load word instruction, whereas the second instruction slot has an add instruction. The condition is instruction branch equals 0 R10L in fact checks the contents of R10, and if the contents of R10, here the following two load instructions, they have dependency onto the contents of register R10 and the value in R8. Now let us see how the code can be improved by using a predicated form of the load instruction, and how we can say that the transformation is speculative. Here, the second load instruction after the branch instruction, that is load R9 from offset value corresponding to contents of R8, it depends on the prior load, that is the load into R8 from the offset value given by the contents of R10. Therefore, this sequence wastes a memory operation slot in the second cycle. Moreover, it will incur a data dependent stall if the branch condition is not taken, as it is quite clear from these two instructions. That is, if the branch is not taken, then definitely it has to have a stall in between before executing the second load instruction, because the second load instruction depends upon the contents of R8, and that is very much not yet available. Therefore, stall is necessary at this place. Now let us see how we can resolve this problem and we can simplify the whole process by using predicated version of the load instruction. Here the load instruction, load R8 from R10 immediately following the branch, can be converted to a predicated load like load conditional R8, the location from R10 with the predicated register R10, and move this value or this instruction up to the second issue slot, that is prior to the branch equal 0 R10, L. The new version of the code will look like this, where it has got 2 instructions issued in the first cycle, 2 instructions issued in the second cycle, and 1 instruction issued in each of the third and the fourth cycle. Note that this particular new version improves the execution time by eliminating 1 instruction issue slot and also by reducing the pipeline stalls for the last instruction in the sequence. In this case, as we are using the conditional move instructions, therefore there is no need for any pipeline stall, which was otherwise needed in the first version of the code. Furthermore, note that if the compiler mispredicate the branch, the mispredicated instruction will have no effect and will not improve the running time. Otherwise, if it is predicated correctly, then it will improve the running time. Therefore, we can say that the transformation of conditional load is speculative. Now, with this much discussion about the conditional move instruction, let us have a view of what are the advantages and what are the limitations of using predicated codes. The predicated codes are extremely useful for, number 1, implementing short alternative control flow, number 2, eliminating some unpredictable branches, and number 3, reducing the overhead of global scheduling. At the same time, the conditional instructions have some limitations, and these limitations are that while moving an instruction across a branch and making it conditional, it will slow the program whenever the move instruction would not have been normally executed. Furthermore, the predicating a control dependent and eliminating a branch may slow down the processor if that code would not have been executed, and the predicated instructions are useful when predicate could be evaluated earlier. Moreover, the conditional instructions results in a stall for data hazards if the condition evaluation and predicated instructions are not separated. The conditional instructions may have some speed penalty compared to the unconditional instruction. Furthermore, the use of conditional instruction is limited when the control flow involves more than a simple alternative sequence. For example, moving instructions across multiple branches require making it conditional on both the branches. So this means that the branching is to be made on both. Thus, it requires to specify additional instructions to compute the controlling predicate. For these limitations, most of the architectures include only a few most commonly used conditional instructions, and the most commonly used conditional instruction is the conditional move. For example, the MIPS, Alpha, PowerPC, Spark, and Intel Pentium all support conditional move instruction, whereas the IA64 microarchitecture, which we introduced earlier, it supports full predication of all the instruction. With this much discussion about the conditional instructions, let us have an introduction to the compiler speculation. Here in our earlier discussion, we have noticed that where the program have branches, and these branches may be predicted at the compilation time, either from the program structure or from the program profile, the compiler speculates to either improve the scheduling and or it speculates to increase the issue rate. However, the predicated instructions may help to speculate. These instructions are more useful when they can eliminate control dependence by using the if conversion. Furthermore, in most of the cases, we would have to move the speculated instructions before the condition evaluation. But this cannot be done by predication. Rather, it motivates us to have the following capabilities to speculate ambitiously. This means that for the ambitious speculation, we must provide the capabilities so that we should be able to find instructions that can be speculatively moved and not affect the program data flow. Similarly, it should also have the ability to ignore exceptions in speculated instructions, and it should ignore them until we know such exception would really occur. And the third one is that it should have the ability to speculatively interchange the load and store instructions, or the store and store instructions which may have the address conflict, because these are the types of instructions which can create problems. Note that the ability to speculate is compiler based, whereas the other two abilities can be achieved by hardware support. The hardware speculation approach supports reordering the load and store instructions. Furthermore, the hardware-based speculative movements of instructions is done by checking for potential address conflicts at runtime, and it allows the compiler to reorder loads and store when it suspects that they do not conflict. For the compile time speculation, we have to preserve the exceptions. For this purpose, there are 4 different methods which are usually used to support more ambitious speculation without introducing erroneous exceptional behavior. Now, the key to all these methods is to observe that the result of speculated sequence that is mispredicted will not be used in the final computation. For this purpose, the exceptions are to be preserved. There are different ways to preserve the exceptions. Let us discuss these basic techniques which are usually used. The first is that the hardware and operating system, they cooperatively ignores the exception for speculative instructions for the incorrect programs, which means that the exception behavior for the correct program is preserved and for incorrect program is ignored. And for this purpose, both the hardware as well as the operating system, they operate cooperatively. Now, this approach is used as a fast mode under the program control. The examples of exceptions that indicate a program error and normally cause termination are the memory protection violation. Similarly, the examples of exceptions that handle the program error and normally resumed are the page faults in the case of virtual memory or in the case of other operations. Similarly, the second approach is to introduce checks to determine when the exception should occur. Whereas the third method is that a set of bits called poison bits are attached to the result registers. These bits are written by the speculated instructions when the instruction causes exceptions. The fourth method suggests that a mechanism is to be provided to indicate that, number one, an instruction is speculative, and number two, the hardware buffers the instruction result until it is certain that the instruction is no longer speculative. Now, with this much introduction to the hardware speculation for compile level operation, we will stop our discussion today here, and next time we will elaborate these techniques in detail with the help of examples. Till then, Allah Hafiz. Thank you.